We now come to one of the most famous theorems called the Pythagoras theorem. Pythagoras, as you know, was living somewhere around 500 BC. That's about 2500 years ago from now. It is said that he was not the first to know or understand that, and perhaps the Mesopotamians and the Indians and the Chinese, they already knew the Pythagoras theorem. But Pythagoras, it seems, was the first to have proved it. That is also a bit hazy because it is long time back in history, but still we take him to be the first one to prove the Pythagoras theorem. And the most wonderful thing about this theorem is this theorem has got the maximum number of proofs, more than hundreds, right? By one account somewhere I was reading, and I saw there were about more than 190 proofs of the theorem, some geometrical, some analytical, but so many proofs. Okay, so we know what the Pythagoras theorem is. So we know that if we have a right triangle, right? So in a right triangle, let us say I have drawn the 90-degree above the at the top. Okay, so if this is 90-degree and this triangle is A, B, C. Okay, so what we are doing right now is the Pythagoras theorem. Okay, we are in fact building the base to prove the Pythagoras theorem. So rather we are a step earlier than the Pythagoras theorem. After we have proved what we are trying to prove, we'll then go on ahead and prove the Pythagoras theorem, right? So we very well know that if this is the right triangle, and this we have been doing since I think class 6th to 7th. So it says that this is the hypotenuse, the side opposite the 90-degree, the right angle is the hypotenuse. So it says that this BC square is equal to the sum of the square of the other side. So AB square plus AC square. Okay. You can choose to call this as base. At times we do that. This as perpendicular, but that is not a very strict choice. You may switch it. You may call this as perpendicular and this as base. Okay. So and this is hypotenuse. So you can also say that perpendicular square plus base square is equal to the hypotenuse square. This is what the Pythagoras theorem is. Now, there is an interesting proof of it which was done by Pythagoras himself that we'll discuss next. But first of all, we'll discuss whatever is given in our textbook. So what we do is, and what we are going to prove right now, the theorem will write later. Okay, so I leave some space for that. And this is deliberate. This I am doing deliberately. There is a reason why I am doing this. Why I am doing this is, many a times when you are told the theorem, you get conditioned. You understand what the result will be. I want you to be organically, to be independently exploring a topic and then come to the conclusion. That is a better thing to do, right? So we just explore, fine. So what I do is I draw a perpendicular from the right angle onto the opposite side. That means I do a construction. Okay, for the time being, I raise these nomenclatures. Okay, they might confuse you. So let us say this is D. This is point D. Okay, this is point D. Okay, and this is 90-degree. Okay. Now what happens? Let us try to explore, and this is very simple. So if this angle is say X, okay, then in this bigger triangle this angle will be 90 minus x. Since this is 90 degree, the sum of the other two has to be 90 degree in triangle ABC, and if this is x, then this has to be 90 minus x, so that when they add up, you'll get 90 degrees, right? Now, if this is 90 minus x, then in triangle ADC, in this triangle, this has to be, this is 90 degree, the sum of the other two also has to be 90 degrees, so this will become x, right? And if this is x and this whole is 90, then automatically this becomes 90 minus x, okay? Now we'll just try to see the triangles, right? So in triangle, okay, so in triangle ABD, this triangle and this triangle, and triangle ACD, okay, let's try to see what happens. So here angle B is equal to, angle B is equal to, these two are the triangles, hope you understand, ABD and ACD. So this angle we see is equal to this angle, so this is equal to angle CAD, angle CAD, and obviously this angle is 90 degrees, so angle ADB is equal to angle ADC. Both are 90 degree by construction, is it not? So they are 90 degree by construction. So these two triangles are similar. Therefore, triangle ABD is similar to triangle ACD by AA criterion. Okay, so these two small triangles into which this perpendicular divided the bigger triangle are similar to each other, right? Now let us try to see what happens if I take this small triangle and the original bigger triangle. So in triangle ABD and triangle obviously ABC, okay, what happens? So obviously angle B is equal to angle B, because angle B belongs to ABD as well as ABC, so they are equal, okay. Now what? Obviously in this smaller triangle, ADB is 90 degrees, so angle ADB, and here it is say equal to angle BAC, because angle BAC is also 90 degree, okay, both 90 degrees. So these two triangles are also similar, so triangle ABD is similar to triangle ACD, again by angle criterion. We have discussed these criterion earlier, right? Actually it was AAA, but since it's a triangle and whenever two angles are equal, the third automatically becomes equal, that's why this. Now we again try to see one of the other smaller triangles in triangle ADC and triangle BAC or ABC, whatever you wish to call, no issues. Okay, so let me call this ABC. What happens? Angle ADC is equal to angle BAC, both 90 degrees, correct? And what? And say one of the angles, say angle C here, is equal to angle C because they belong to both the triangles, the ADC as well as BAC. So common to both triangles. One thing we should understand whenever we are doing the proof, whenever we are writing something, it should always be qualified by some statement or the other, right? So they are also similar. So we say that triangle ADC is similar to triangle ABC again by angle criterion. Okay. You can write it as AAA as well, but we have seen you do not require to do that. Okay, so what have we essentially seen? Whenever there is a right triangle and from the right triangle, from the vertex that contains the right triangle, we draw a line perpendicular to the opposite side. In this case, it becomes the hypotenuse. Then the three triangles, it divides it into two smaller triangles and the original bigger triangle already is there. So whenever that happens, then all these three triangles, the original bigger one and the two smaller ones, are similar to each other taken two at a time, right? So what should the theorem be? The theorem should say that when we draw a perpendicular from the right angle of a triangle to the opposite side, the three triangles are similar to each other taken any two at a time. Do we get that? Now this is a very important conclusion that we have drawn, and this will help us in proving the Pythagoras theorem, and that will be only one of the ways out of all those about 200 ways in which it has been proved. Okay, and that is what we'll do the next. Thanks a lot.